Alright, I think we're recording now. So, first time working with this, I'm not that good at it. So, welcome to this lecture 13 today. And I'll be trying to go through this topic, quite a short one. It's like only 6 slides worth of content or 5, but it's super important in Olympiad geometry. So, it's about power of a point with respect to a circle. So what does this mean? Before I get into that, actually, I just want to let you guys know that why I say this is quite important is because this is not a very hard topic, but a lot of the times in normal school setting, you don't learn about power of a point, at least not in regular geometry lessons, right? So let's get right into it, and you'll understand it quite easily, I think. Okay, so the first theorem that we need to know, there are a total of like 3 theorems today that you need to know only, that's why there are 5 slides. The first theorem is, I'm just gonna call it theorem 1, there's actually not a name for it. It's not something that someone discovered and then hence it's credited to the person. Let me just call it theorem 1, okay? So basically what it's saying is, let omega or w be a circle with radius r. Just draw it out here. It's easier to see, right, if I draw it. Oops, wait. I hit a button accidentally. Okay, that is a shit circle. Let me just remove it. Let me at least try to draw like a more decent circle. Okay, so let this circle, let's just name the center O. It has radius r, okay? So from an interior point P of the circle, what this means is that you randomly choose one point. Let's call this point P. Okay. If AB is a chord passing through P, let's just draw any random chord AB passing through P. Okay, so let's name it A, let's name this B. It passes through P. Then the product PA times PB. So basically P splits this chord AB into 2 parts. PA times PB here is independent of the choice of the chord passing through P. So what I'm saying is that, okay, in this case I chose a random chord AB, and we have the value of PA times PB. If I were to choose another random chord, let's do this, okay? Random one. Let's call this C and call this D. What it's saying is that PA times PB. Oh, why did I write 2 B's? Oh, sorry, let me just switch to an eraser. Okay. So PA times PB will be equals to PC times PD. So it's saying that no matter what chord we draw, as long as it passes through P, like the P splits any chord into 2, I won't call it halves because it's not exactly half, but 2 regions. The length of the 2 regions times together would be the same for any chord that you choose. So that's the theorem. And specifically, this theorem is saying that these products all have a value, a fixed value. So the constant value here is given by assuming AB perpendicular to OP. So what it's saying is, let me just remove everything from the screen again. and redraw something. So you want to find the constant value of the products, right? Products of regions of chords. Well, I tell you a very simple way that you might want to find the constant value. If I tell you that's constant, why not you choose AB like this, you choose P to be in the middle of AB such that OP, this line, is perpendicular to AB. So you know that this OB is R and OA is also R. Okay, now we want to find the constant value, right? So we want to find PA times PB. And in this case, since we split PA and PB, it's the same thing, which is equals to PA squared, because it's literally PA times PA also. So just look at PA, okay? If we're focusing on PA, we get this triangle. So here's O, here's P, this is A, and this length is R. So what is PA squared? In fact, by Pythagorean theorem, if you apply it to this triangle, you get PA squared plus OP squared equals to R squared. And when you move R to the other side, PA squared equals R squared minus OP squared, which is where this formula comes from. That's a constant value. Alright, so let's move on to the next slide. This slide is basically the same. This is theorem 2, but it's almost the same thing. What it's saying is that, remember last time we got this setup: a circle, a chord, and a center O, and then some point P, which is inside the circle. For theorem 2, we're looking at the fact that what if P is not inside the circle? In fact, it's either outside or on the circumference of the circle. So let's take a look at what happens. Circle here, O, let's say P is on the outside, right? And then same thing, you get a chord, but in this case it's called a transversal because it cuts through from point P to 2 points of the circle. So let's just pick any line, let's just say this, cut like that. So P, let's call this A, let's call this B. So this is called a transversal. It's just a line connecting P, cutting through the circle in any way. And when it cuts through the circle, it will cut through at 2 points naturally. So it intersects at A and B, and then what this theorem says is that the value of PA times the value of PB would be independent of the choice of transversal passing through P. So what it's saying is that in this case, let's say you draw another random transversal passing through P, and we got C and D here. What it's saying is that it doesn't matter which line that we randomly drew, but PA times PB will be equals to PC times PD. It doesn't matter which line we draw it through, would be equals to some constant value. Let's call it C. Yeah, it really doesn't matter. Let's say we drew it here. Let's call this X, let's call this Y. PX times PY would also be the same as PA times PB and PC times PD. So what we want to find now is actually, in fact, what is the value of this constant that it is always equals to. So from just now, you saw that to find the constant, we set up a specific case that makes it more convenient for us to find the constant. And this case is the same thing. So let me just erase the clutter on the screen again. In this case, the constant that we're hunting after is PA times PB, right? But let me just show you how we can set it up for ourselves very nicely, such that PA times PB would be solved very simply. Let's call this point P also, same setup, but let's draw a very special and unique case of the transversal, which is this. it's more or less, yeah, it is tangent to the circle. Let's call this O again. Center is O. So this transversal, so you might be thinking, wait, if it's tangent, it cuts through the circle one time. But this part, it says cut the circle at A and B. Well, when it cuts through the circle one time, what it's saying is that both point A and point B is at this point. Okay, compared to when you cut through like this, for example, point A would be here, point B would be here. But if you cut through at one point only, point A and point B would be on the same line. I mean on the same point, sorry. So now what do we get? We want to what? PA times PB. What is this equals to now? If PA and PB are the same, I mean if A and B are at the same point, so PA will be equals to PB. So this will be PA times PA, which is PA squared, right? So now this constant would be just PA squared. We want to find PA squared. So if you realize, right, if you drop perpendiculars like this will be perpendicular, right? This length would be R, and OP is this length. Consider this triangle and do Pythagorean theorem. You realize that OP squared equals to PA squared minus R squared, and then you just add R on both sides. You get PA squared equals OP squared, oh wait, I mean plus R squared, sorry, minus R squared. You subtract R from both sides, which is this form. We found C. Let's just make it more explicit. We got C here. Alright, so next up, consequence of theorem 2. So what we just learned can be applied to some questions. What it's saying is that when line segments, let's say you have line segments AB, so AB and CD, or their extensions, this is in like their extensions, okay? AB extended, CD extended, intersect at P. Then ABCD are concyclic if and only if AP times PB is CP times PD. So what I'm saying is that if these are concyclic, then we can make use of theorem 2, the latest theorem that we learned, that says that PB times PA is equals to PD times PC, which is here. And if this result is not true, if it's found to be not true, then A, B, C, D not concyclic. That's all. That's all that's saying. This is the practical application and the questions that you can see. Alright, now next up we got radical axis. Also another thing that's not very commonly seen. This is also kind of related to the power of a point, what we just covered. So what it says is that for any two non-concentric circles, so non-concentric, right? Concentric means something like this, one circle and the other. Okay, so this is concentric. Non-concentric means anything that's just not like that. So it can be like this, can be like this, can be like this, any two things. Yeah, so that's the explanation for concentric. Okay, let me just leave concentric here just in case any of you need any reference. Okay, so the locus of all points with equal powers to the two circles is a line called the radical axis of the two circles. So if you have two circles, what I'm saying is that there is a line that at any point along that line, that point would have equal power to the two circles. So that's how you would phrase it in a easier way to understand. Alright, that one's nothing much actually, but now we extend it to something called the radical center when there is three circles. So when there are two circles, remember that it's called radical axis. Right now it's called radical center. So radical center is basically when the three centers of the three circles are not collinear, there exists exactly one point whose powers with respect to the three circles are the same. And this point is called the radical center. So for any three circles, if any two have a radical axis, then the three radical axes may be parallel to each other or concurrent at the radical center. So for example, let's just draw one circle, two circles, and three circles. So you realize that between any two circles that exists a radical center, a radical axis. Let me just use, is there a different color that I can use? Yeah, okay. So now I have green. So between let's call this the left and the right one, we have this radical axis. Okay, what I'm saying is that between any two circles there is a radical axis, right? So let me just use, I'm gonna keep switching colors to make it simpler for you to understand. Colors are good, right? Between the top and the right one, there exists this radical axis, and between the top and the left one, the radical axis is this. So it's saying that the radical axes are concurrent at the radical center, which is here. This point is called the radical center. Okay, so the logic is, if between any two circles this point has the same power, that means it has the same power with respect to all three circles, hence it is the radical center. Now moving on, just some key properties of radical axis. Now we're back to radical axis. If you're wondering why, it is because radical axis is usually more important of a concept than radical center. The reason is radical center is not very commonly used because it involves three circles, but radical axis is a lot more commonly used. If you are flipping through questions regularly, you see radical axis a lot more. So things that you have to note: two different concentric circles have no radical axis. So concentric, again, it is one circle in another. In this case, it has no radical axis, right? So where it exists is that if it is not concentric. So if it's not concentric, a radical axis exists, and we're looking at three cases, okay? So the first case is two separated circles. These separated circles, we'll look at it like this, for example. Okay, the radical axis is the line perpendicular to the line joining the centers of the two circles. So that's the first property, center 1 and center 2, and there is a line joining the centers of the circles. The radical axis will be a line perpendicular. So that's the first clue that we need to know how to look for the radical axis of two separated circles. Next clue is that it passes through the midpoints of the four common tangent lines of the two circles. What that means is, let me just switch ink again because everything in red is very boring, right? Okay, so what it's saying is that there are four tangent lines between the pair of circles every time. Just take note, This is not that nice. Hold up, let me just pull out the eraser. And okay, switch back to the pen. So we have this tangent line, we have this tangent line, common tangent lines, okay? We have this, and we have this. So these four common tangent lines, they each have their midpoint between the two circles. So here, here, and here. What I'm saying is that the radical axis would just be the line passing through the four common midpoints. Maybe I shouldn't use green to label, but a bit unclear. But this line is the radical axis, the one that's vertical, and it's perpendicular to the red line joining the two center of the circles. Okay, so this is the most complicated one, and the rest is easier. Let me just erase all the ink, switch back to red color. So now we're looking at the case 2, right? Case 2 here. For any two intersected circles, this one is super simple to identify. So if you have two separated circles, for example, intersected circles, my bad. If you have intersected circles, it is the straight line passing through the two intersections. So it's literally a straight line passing through the two intersections. This one. This is the radical axis. Okay. Now the last one. If any two circles are tangent to each other, this is also very simple to identify the radical axis. Two circles, they are tangent. Okay, this is a very bad drawing of a tangent. I need to erase this. Okay, so let me just try to draw this properly. Okay, just take that tangent. I don't really care anymore. Yeah. Alright, looks good to me. If they're tangent to each other, so they touch at one point, the radical axis is just the tangent to that common point. So the common point is the intersection point, that a singular intersection point. So the radical axis is the tangent to this. This is radical axis. It might not look tangent, but yeah, just trust me, it's tangent. So this is how you identify the radical axis for two circles in any two different configurations. So you have two separated circles, two intersected circles, and two tangent circles. Now you know how to identify radical axis. Okay, so now we've come to the end of the lecture, and here's my email in case you can email me anything you want, any questions if you have. And that's all. For the next lecture, we're going to be looking at the example problems and also probably some sample problems for you guys to do. And so yeah, that's it for this one.